Hello, and welcome again to Data Science Foundations. Today we're going to be learning one of the most important concepts. Sort of after this point, I feel like you will have learned half the material. There will be one other sort of foundational class later on that we also get sort of a very big principle. But today we're going to be learning about the plugin principle. Once we learn about the plugin principle, and this is why I love it, we'll be able to extrapolate, we'll be able to use this to tell us lots more things about data, data science, machine learning, and inference. So let's get started. What's very important for the plugin principle is that we have our assumptions. Okay, these are again foundational assumptions, and when people ask me questions like, what do we do when we have missing values? What's a good thing to do if we believe that our data is biased in this particular way? You go back to your assumptions, and then using the knowledge of the assumptions, you can make pretty educated guesses on what's best to do. People without the knowledge of these foundational assumptions tend to rely on heuristics, and these can lead them to make sort of dreadful decisions, I think. So let's go back to the assumptions. So the assumption number 2 is we have data. So we have the data. That's kind of important. And assumption number 1, we have IID samples from a random variable x. And we learned what a random variable was previously. A good metaphor to describe it is it's simply a function that returns numbers. We learned what samples were. Samples were simply calls of that function. And we learned what IID was. And IID is incredibly important. So IID is basically your assumption that these samples are drawn randomly. Assumption number 1, so it's independent. Independence means that these samples don't depend on each other. That knowing some information about one sample doesn't give you any extra information about the other sample. Independence is pretty crucial. It's not completely crucial. There are some times when we can get by without having independence. For example, time series analysis, where one sample does depend on the previous sample. And then, of course, identically distributed. If you don't have identically distributed, you're going to be in a very strange realm. Identically distributed basically means that you're getting your data from the same distribution. The typical example of this is in the Truman elections. So during the Truman elections, pollsters would go out and they did polls. What they did is they went in the telephone book. They picked out random numbers or random telephone numbers, and they called those people. And when they called them, they asked them, like, hey, are you going to vote for Truman or not? And so people did this. They did this lots of times, and they got a very high statistical significance in terms of in favor of Truman. So they did their bootstrapping, and they were like, oh, wow, Truman is not going to win this election. There's no way. And so they went ahead, they printed the papers beforehand. And of course, Truman, sort of won in not a landslide, but won fairly handily the next day. And they were like, what went wrong? Can you see what went wrong? The idea here is that they weren't sampling Americans that would vote tomorrow. Instead, they were sampling Americans that would vote tomorrow that had a telephone. You were working with the wrong distribution. So in this case, you were trying to extrapolate from one distribution onto another distribution. So I guess you could say that the samples weren't identically distributed. So these are both very, very important. There are things that you can do in violations of both these assumptions, but let's stick with them because we'll get really far with them, and then later on, perhaps in sort of a version 2 of the class, we can talk about this. Okay, so now we're ready to get to work. Once we have our assumptions, we can use the plugin principle. So let's start off with the basics. So, for example, we were asked a question about our population distribution. And the question would be, what's the height of all people in the world? Right? And if you had enough money and enough time, you could just find this out. You could survey every single person in the world. It would cost a ton of money. It would probably take years to actually get all this information. But you could get it. You could eventually get it. And you could know exactly what the average height of people in the world is. Okay? But generally, you can't. Sampling that many people is way too expensive. And as well, sometimes you just can't do it. For example, if you want to know what future customers will do, you can't sample future customers. They don't exist yet. So one way to get around this, one way to be able to answer questions about your population is to use the plugin principle. Excuse me. So let's get started. So let's say we're trying to figure out, and so this is going to be sort of an arbitrary thing. Let's say we're trying to figure out how many trees are in each person's backyard. Okay, pretty simple question. Maybe we live in like Minnesota or something like that, and there's not that many people here, and so the total population is of size 1,000. So there's 1,000 people in the population. I can show you what the population would look like. So there's 1,000 backyards. Each backyard will have maybe 0 trees, maybe 1 tree, maybe 1 tree, something like that. Normally, you wouldn't have access to this information. So normally, you would only have access to a sample. So a small subset of the population. So for example, I get a sample here. And my sample has 10 yards. So I went around to 10 yards, randomly chosen. And I got a sample from them. Okay, now it's time for the question. Now the question, how many trees are in people's backyards, is kind of, it's not very specific, right? You need to actually be able to answer how many trees is in everyone's backyard. You need every piece of data to figure that out. So instead, we generally phrase our questions in terms of summary statistics. So we talked about summary statistics previously, and this is why we did. So what's the question I'm going to say? Well, the question I'm going to ask, in broad terms, we want to find a function of our population. We want to find a summary statistic of our population. In this case, I'm just going to go ahead and say that we're looking for the median number of trees in backyards. It could be anything. You could take the average. Median is a little bit more robust to outliers, so I like using median a little bit better. We have our assumptions. Our assumptions are that we have a sample from the population and that those samples are IID. Okay? So we have the question. We have our assumptions. We're ready for the answer. What is the answer? The answer is the plugin principle. And this is super simple. You guys probably already guessed it. The best guess as to what the function would be applied to the population is applying the function to the sample. Really simple. So if you want to guess what the average IQ of Americans was, getting a random sample of Americans and asking them an IQ test, and then averaging that would be a good estimate, would be the best estimate for the average IQ of Americans in general. The Proofy Statement is as follows. In a non-parametric framework, the empirical distribution, aka the sample, is a minimum sufficient statistic for the true distribution, aka the population. In this case, the plugin principle provides the non-parametric maximum likelihood estimate. So this is it's kind of deep. So back in the day, one of my favorite books, textbooks, let me just sort of phrase that, not one of my favorite books of all time, was Introduction to the Bootstrap. This was written by Efron. And I was so excited about this. I read this book, I think, like 3 times. I even emailed Efron and asked them questions. And one of the questions was kind of this. It was kind of like, hey, where's the proof? Well, like, I get the plugin principle. Hey, if we have, I guess, sort of the intuitive explanation is that if the size of the sample were the size of the population, right? So if the size of the sample were the size of the U.S., obviously the average IQ of the U.S. would equal the average IQ of the U.S., right? But as the population size gets smaller, or the sample size gets smaller and smaller, is it still true, right? And so we talked about this, and this is kind of like the sort of proofy statement that he had given me. So hopefully it helps you that are a little bit more inclined towards proofs. So anyways, if you've got any questions about that, please go ahead and comment below. I'm not going to spend much more time on it because I believe it's a little bit, plugin principle is a little bit intuitive, and honestly, I think just taking a small leap of faith with this one, I'm only going to ask you to take 2 leaps of faith in this class, and this is one of them, is perfectly fine. So there's 2 things you need to know about the plugin principle. One is the trade-off. So the trade-off is pretty important. So as the size of the population increases, or the size of the sample increases, the better the plugin principle will be. And this is, should make sense. If the size of the sample is the size of the population, the plugin principle will be the exact right thing. If the size of the sample is only 1, then, well, it could be pretty bad. So that's first. Second, this is the big catch. While the plugin principle may be your best guess, it does not mean that it's a good guess. And this is somewhat unintuitive, right? But it basically is just one of those things. Sometimes you just can't know much. So even though you have a best guess and you know what your best guess is, that best guess might be a terrible one. Okay? And so that's the big catch of the plugin principle. So now that you know this, let's get some experience using it. So we try it out with a very simple function, in this case, the median. So I go ahead, I find the median of the population distribution is 0, median of the sample, it's 0. Good estimate, right? Okay. Let's do a more complex function. Okay. So let's say I was interested in the chance that any 10 randomly chosen yards would have no trees in them. This is a pretty complex function. Okay. So it's kind of like, hey, I was interested in like if I were to choose 10 random yards in Minnesota that no people would have any trees in them, or that none of those yards would have any trees in them. You might be interested in this because you are, part of the Environmental Protection Agency and you want to reach out to 10 random people and you want to make sure that at least some of these people care about having some foliage in their backyard or something. But it doesn't matter. This is what we're interested in. So what is this? This is a function of our population. It's actually a random variable of our population because we randomly sample things and we return a number. So let's write that random variable down. So in this case, the random variable will be, take our population, we go ahead and we sample 10, so we sample 10 things from our population, so 10 backyards from our population. We get this random set. We see if our random set contains no trees. If it contains no trees, we return a 1. And if it contains trees, we return a 0. Okay? Pretty simple. So it's a random variable. So I return some numbers, in this case 1 or 0. I return 1 if my condition is satisfied. In this case, the condition is, hey, those 10 trees that I randomly selected had absolutely no, or those 10 yards had absolutely no trees. I return 0 if, hey, those 10 yards had at least one tree. Why did I choose 1 and 0? So in this case, it's kind of nifty. But if I take the average of lots and lots of these runs, then I actually get the probability of this happening, right? And you can sort of see this. If out of a billion runs, one of them actually went ahead and returned that they had no trees, then I would estimate that on average, every 1 billion runs, I get one that had no trees. It's kind of like the chance that this would happen. So let's sort of run this ourselves. So this is a random variable. We can go ahead and try to find the mean of a random variable by taking lots of samples from it, as we talked about before. And so 10 yards, no trees. I go ahead and I sample this about 10,000 times, and I find the mean. And I go ahead and I get something like 0.8%. So 0.8 or 0.9%. Would sort of be like the average number. So this would be the chance that you would sample 10 yards and get no trees back from them. Okay. Pretty cool. Now here's the question. We were able to do this with the population, right? So we had the population in this case. Can we do this with just the sample? Okay, well, I said that the plugin principle was great. All we had to do was we had to take the function and apply it to our sample, right? So maybe all we need to do is take this very complex function that we created here, which was randomly selecting lots of times. So in this case, this is randomly selecting 10 things from our population distribution and select it lots of times and then find the mean of that. That's kind of like a very complex function. All we need to do is we need to apply it to our sample. Easy, right? Do you see any problems? There should be one problem that we're going to solve this lecture. So there's a small problem. What if we randomly pick 10 trees from our sample that is size 10? Well, it would be the same sample. In fact, it would be no variation. In fact, it would always return it has some trees in it because our sample had some trees in it. There's a little trick that we can use to get away with this. So it turns out there's something called sampling with replacement. And I've done a video on sampling with replacement and sampling without replacement that I'll link. It will probably be up in the top right-hand corner of the video. And so sampling with replacement or sampling without replacement, you just imagine you've got this big old bag full of whatever marbles, and you take out the marbles and you sort of record what color they are. Sampling with replacement is you take a marble out, you record what color it is. Hey, this yard has no trees, and then you go ahead and you put it back in, and you repeat. And so in this way, it's kind of like a pseudo sample from the population. It turns out it has a lot of the same properties as sampling without replacement, and so we can get away with using it. And so this is often called bootstrap sampling, and we'll sort of see why in a minute. Well, not in a minute, but in a lecture or two. So we go ahead and do this. So I make a new random variable, 10 yards, no trees. I sample from the sample. Okay, in this case, I make sure to sample with replacement. The random variable is the same otherwise. And I go ahead and I sample from it 10,000 times. This is the exact same function that we applied to our population, except for we're sampling from the sample now, right? And the sample from the sample is with replacement. And ta-da, we get an estimate. So in this case, we get 6%, or 0.6% instead of 0.9%. So there's a little bit of a difference, right? And one of the reasons why there's such a big difference is because our sample size was quite small, being just 10. But as that sample size increases, it will get better. Okay, so I want to just sort of take one moment and step back, tell you something that I find very interesting about this. So if you remember, if we go all the way back up here, I just find this very cool. You could have kind of predicted the plugin principle would happen. Okay, why? How could you have predicted that? Well, we talked about random variables before, didn't we? And if you remember, we talked about trying to find the mean or summary statistics of a random variable. What do? Well, simply, you sample lots from the random variable. And if you sample like 10,000 times or 1,000,000 times, you go ahead and you get a really good estimate as to what that would be. Whatever that function you would be interested in, whatever that summary statistic of the random variable you'd be interested in. You take lots of samples, you use those as kind of like a little data set. You find the summary statistic on that little data set. And then ta-da, you get an estimate for what it would be on your population. Pretty cool. Well, what did we say? What did we say? So we said the population was a random variable X. We said that we were identically sampling from that distribution. We kept sampling from that distribution, right? And these samples were independent. This is not super important here. But we have lots of samples from a random variable X, right? Now, what if we wanted to estimate a function, a summary statistic of that random variable X? What would we do? You'd sample it lots of times, right? And then you'd compute the summary statistic on those samples. So in a sense, you can think of a plugin principle kind of like, well, it's kind of like the population is a random variable, and you want to find the summary statistics of the random variable. The plugin principle is very similar to that. It's sort of got this, I don't know, this really great parallel that I see here. So I don't know if that sort of helps you remember it, but it's something that I kind of like. The plugin principle is like comes throughout in what I'd call sort of computational statistics. Okay, let's go ahead and finish this up. I want to sort of ask the final question: why is this important? So we've learned what the plugin principle is. We've learned what questions it answers. We've got some population. We're interested in summary statistics on the population, and we only have the sample. What do? Well, we apply the summary statistic to the sample, and we say that's our best guess. Okay? We can easily see how important this is. In order to make inference, in order to learn things about a population that we haven't seen before, this is the only tool we have, right? It's the only tool I've taught you. So it's incredibly important. We'll actually see how it's also important in machine learning, because this is a tool that allows us to say that we can learn in machine learning, which is crucial. Now there's the catch and the trade-off that we need to always be cognizant of. The trade-off, the more data you have, the better the plugin principle will be. And the catch, which we'll solve in the next couple of lectures, the catch is, even though it's the best estimate, it might not be a good estimate. So how do we solve that? You know, maybe the plugin principle is the best estimate, but it's always terrible. And so, well, we're still up a creek without a paddle. Okay, so hopefully you've learned what the plugin principle is. Hopefully you've heard more about it than you'll ever want to. Well, fortunately for you, we've got a couple more lectures that are all based on the plugin principle. I think until lecture 11, it's going to be super plugin principle based. So hopefully you learned that and you know how to use it now. I'm going to give a ton of questions down here about using the plugin principle and how it works. So as always, here are the comprehension questions. If you're interested in answering any of these questions, go ahead and comment down below. I'll go ahead and respond to your comments with what I think, whether they're right, whether you need to sort of refine them a little bit. If you see someone who's already answered something similar to you, just go ahead and give them a thumbs up. That way we don't sort of clutter the comment section with these sorts of things. Okay, so hopefully this was awesome. Next time we're going to be finally getting into Bootstrap. So I hope you're excited.